Hey everybody, welcome back to the channel. We are talking anatomy and property of waves today. Previously we had looked at periodic motion, which is wave-like in nature, and it gets into some of these concepts like we talked about period a little bit, we talked about amplitudes, things like that. This time we're talking much more in depth. We're looking at kind of just all of it and not just that particular type of motion. Trying to get down with what this all is. So one of the things that you can talk about when you're talking about waves is a transverse wave. Transverse waves are pretty much what we were looking at last time, where you have this kind of classic wave form. It's got this sinusoidal shape. Ultimately, you are moving perpendicular to the direction that the wave moves. Okay, so the particles of the medium being the material that the wave travels through. Okay, you're going to move perpendicular to that. So in the case of this picture here, we have a rope. The rope is connected to this wall, and some guy's got his hand on it, right? He waves the rope up and down. Okay, the rope itself is going left to right, but he waves it up and down, and as a result he's sending what's called a transverse wave through the medium. That wave is going to move perpendicular to the rope. You can, however, do what's called a longitudinal wave. Okay, now, in a longitudinal wave, I move parallel to the medium. So here you've got the same sort of situation, but instead of a rope, we've made it into a slinky. And we actually have a slinky lab where you're going to get to do this. You actually make both transversal and longitudinal waves with slinkies. It's kind of fun. And a good way to just kind of chill out a little bit and have kind of a relaxing lab, where you basically just get to play with toys. Okay? So a longitudinal wave basically causes there to be what are called rarefications and compressions. So if you look at this picture, there's a point where the slinky is compressed. So the coils are really tightly together. And there's points, those are obviously compressions. No worries. Rarefication is probably a less familiar term. I only remember it for talking about waves. Because you just don't deal with it normally. So rarefication would be when it's all stretched out. Okay, so I remember that's a little more rare because normally I'm compressing stuff. I'm compressing my air into tires. I'm doing a lot of stuff with compression all the time. You don't really stretch things out that way. So the word's a little more rare in my vocabulary. Ha ha ha. Rarefication. All right. So ultimately, you're removing parallel within the medium. So the direction of the wave is parallel to the medium itself in a longitudinal wave. You can also have other types. There's surface waves. This is like ripples in water. Sometimes called a circular wave. And this literally is just a wave that's traveling along a surface like in a body of water. And ultimately the particles in the medium are doing like a circular motion as a result of this. We don't really go into a lot with surface waves in our class, but they are out there. They are really awesome and cool. Throw a rock into Folsom Lake, and you're bound to see some surface waves and get that circular motion going. Now, waves can be broken down into two categories. We have electromagnetic waves. So electromagnetic waves are waves that can actually transmit energy through a vacuum. So light from the sun comes to us from the sun because it's an electromagnetic wave. It can travel through the vacuum of space and get to us, and we can actually see stuff, and we get all the colors, all these kinds of things. All that stuff's actually coming through electromagnetic radiation. You've got things like your microwaves. You've got lots of different EM waves. types that we deal with. We're probably going to go into this a bit later. I do have a cat toy and jello lab for us to kind of dig into these sorts of things and see how those work. Mechanical are a lot easier to create in the classroom. You made mechanical waves already with pendulums. We're going to make mechanical waves with slinkies. Realistically, water waves, if you've gone and watched some people like surfing, those kinds of things. Doing the wave in a stadium, jump roping, all that stuff. That's all mechanical waves. So big difference between them being that the mechanical waves are not transmitting energy through a vacuum. They're moving through a medium. Okay, so there's a medium involved. That medium is like water or a slinky or the rope of a pendulum, these sorts of things. Those are all mediums that a mechanical wave can travel through, while the electromagnetic stuff is really coming to us from distant places, traveling through vacuums, stuff like that. So the medium, since we've been talking about this a lot, a medium is the substance that carries the wave. So ultimately, it's a collection of particles. And it's really kind of important to understand that the medium itself does not make the wave. Okay? The medium carries the wave from whatever created it to another location. Okay? So a wave is really moving through the medium, but the medium itself doesn't actually move. It's kind of cool. So really what's happening is that a wave is transporting energy from one place to another, not the matter itself. So ultimately, when I send a wave through a rope, right? So there's two people, we're holding ends of rope. I raise up my hands and lower it down, and it creates a wave. That pulse of energy is going to go out until it hits the other person, and it might come back at me a little bit. Okay, we'll get into those sorts of phenomenon in a later video, but that's the key concepts of using a wave, right? Ultimately, the rope didn't move. That might be a little weird to you. The rope, once the waves passed, I'm still holding the rope. The rope stayed in the same place. The particles of the rope have gone back to being the way they were. I didn't move the rope. I sent a wave through the rope. I sent energy through the rope. But the rope itself stayed where it's at. Okay? So think about baseball for a minute. If I'm playing baseball and I take a baseball bat and I smack a baseball out into the field, I've moved the ball. The ball is no longer where the ball was. Okay? At the end of its travels, the ball is going to be somewhere in the field because I used the force of my bat to smack the ball to another place. I've transported matter when I'm playing baseball. But when I'm jumping rope, when I'm creating a wave with a jump rope, I am not, in fact, transporting where the rope is. I am making waves within the rope itself. I'm sending waves through a medium, and those waves are energy that's going through it. And you might see a distortion as the energy passes through it. And it might look like it moved up and down and stuff like that, which it did. The particles moved up and down, absolutely. However, at the end of the day, the jump rope is going to stay where it was. It's going to settle down, the energy is going to dissipate, and the rope will be in the same place. All of the particles of the rope are in the same place as they were when we started this wave. Folsom Lake does not move to another location, even if there are waves going through it. Okay? Eventually, it settles back down, and the waves stop. That's kind of a key concept, that a wave transports energy. A wave does not transport the matter. So we kind of looked at transverse wave anatomy a little bit in the previous video. We talked about crests and troughs, crests being the maximum displacement upwards, a trough being the maximum displacement downwards. We have the height of a wave that we could talk about. We have the length of a wave that we could talk about. So the wavelength obviously needs to go from point to point. And those points need to be the same. So if, in this case, points A and B are being drawn from crest to crest. Okay? You could draw the wavelength at another point, as long as you're going back to that same point. You're completing that motion of going up and going back down. Okay? The wave frequency is the number of wave crests passing point A each second in this particular picture, while the period would be the time required to go from A to B. So the time required to go one full wavelength is the period, while the frequency is how many waves go through each second. Very closely related values. And we're going to use that mathematical relationship here in later on in this video. Right. Longitudinal waves, of course, deal with the compressions and rarefications. So ultimately, if you're looking at this particular picture here, you can see that there's compressions going on at A, C, and E, and you can tell that because the coils are much closer. While rarefication has the coils pressed apart or split apart, and that's occurring at points B, D, and F in this particular one. Frequency and period. Okay, so frequency, think about how frequently you do a thing. How frequently do I mow the lawn? How frequently do I brush my teeth? You know, if your frequency of brushing your teeth is 3 times a day, you're doing pretty well for yourself, okay? Hopefully you take a shower every day, these kinds of things. The Earth goes around the sun 365.25 times, the Earth goes around the sun once every year. Okay, the period is how long it takes to do a thing. So the period would be 365.25 days to complete a cycle around the sun. Okay, so the amount of time it takes for a thing to occur. I brush my teeth every 8 hours, for instance, would be a period, not the frequency of how many times do I do it in a day. Okay, how long does it take versus how many times does it occur? Very, very closely related, and you can see it in the equations. Period is 1 over frequency, and frequency is 1 over period. Okay. Energies. So we talked about this particular thing. Energy is related to the amplitude. Okay, the higher the amplitude, the higher the energy. So a wave with a lot of amplitude is transporting a lot of energy. Okay. If I am not transporting a lot of energy, then I have lower amplitude. Think about throwing a rock back into the lake. Okay, I throw a small stone into the lake, I create small ripples. I throw something pretty massive with a lot of force, I hit the wake, I'm going to make a much bigger ripple. Much more force went into the throw, much more energy is going to come from it. I'm going to create a bigger wave. Okay, big, huge, crazy waves can be very destructive and are carrying a lot of energy. Ultimately, energy is proportional to the square of the amplitude. Okay, energy is proportional to the square of the amplitude. So this is ultimately, if you had 2 units of energy, you're going to have, or 2 units of amplitude, you've got 8 units of energy. You're squaring the numbers, more or less. Here, you got this energy amplitude relationship, ultimately, and if I go from 1 to 2 units, I'm going to increase a 2-fold increase in amplitude would create a 4-fold increase in the energy. A going from like 1 to 3 units, I create this ninefold increase in energy. Ultimately, you get out a lot more energy, and it's working on this kind of a square relationship. Now, distance equals rate times time. We did this a lot. Okay, we did a lot of D equals RT in this class. We've been doing it since January. It's kind of one of my favorite things because I really enjoy problems where trains are leaving a station and all this kind of stuff. Now, ultimately, waves are going to work very similarly. They're still going to obey distance equals rate times time. Okay, but we're going to talk about rate, and we're actually going to talk about rate in terms of the speed. Now, the first thing you want to know, if you want to make a wave go faster, is that nothing in the wave itself is going to make a wave go faster. So increasing the amplitude of the wave does not make the wave go faster. Increasing the time it takes, increasing the amplitude or any of the other properties doesn't make it go faster. What does make it go faster is if you change the medium. So the way you make a wave speed up is you change the tension in like a rope. So let's say you and your friend are holding a rope, and the rope's really loose, and you put a wave through it. Okay, that's going to get a certain speed as the particles interact. It's ultimately particle interaction that is causing the energy to go from the source to another place. Now, let's say your friends and you hold that rope tight and taut so that everything is there's no energy lost. It's very, very tight ropes. You give it another wave. That wave's going to go through, and it's actually going to go through faster. The medium that the wave travels through is the most important thing for the speed. It's the only important thing. Changing the medium will change the speed of a wave. But again, that ultimately works on distance equals rate times time. D equals RT. So instead of D equals RT, let's go ahead and call rate speed. Now I'm going to solve D equals RT for rate. Okay, I do that by dividing by time. So I divide by time on both sides. I got distance divided by time equals rate. But I'm going to call rate speed. So speed equals distance divided by time. All right, cool. No worries. Speed is distance divided by time. Now, the distance that a wave travels, well, we call that the wavelength. Okay. And the time it takes to travel, we call the period. So let's replace distance and time with wavelength and period. So speed equals wavelength divided by period. Speed equals wavelength divided by period. Remember I kept telling you that frequency and period are really closely related. Obviously, frequency is 1 over period. Well, 1 over period is kind of what I have. Wavelength divided by period would be the same as wavelength times 1 over the period. But 1 over the period is frequency. So speed equals wavelength times frequency. And we write that with that lambda letter. So V equals F lambda, or speed equals wavelength times frequency, is the wave equation. That's probably one of the most important equations that we're going to be talking about as far as figuring out the speed of a wave. You're going to get a lot of problems with this particular problem. You are going to see this weird lambda character, so it's time to wrap our heads around just a few Greek letters. That's fairly important at this stage. We're getting to where a lot of Greek letters are going to be starting to show up in your math and in your science. So it's time to accept that sometimes we're going to make these characters. It looks like an upside down V with a funny hat on. Okay, that's my lambdas. That's really about it for this particular video. There's more to talk about with waves. There's lots more that we can get into. But this particular video had a lot of vocabulary, a lot of important words that we're going to have to learn. I will try to make some tools for that, maybe on Quizlet, to help you out. But ultimately, there's a lot to get down when it comes to waves. So hopefully we at least introduced you to some of the language. We introduced some pretty important equations. We showed how we got to the wave equation, which is probably the most important equation when you're dealing with these things. And hopefully I made some sense out of some of the stuff for you. And ultimately, folks, just start learning the vocab, and this will become a lot easier. That's about all I got to say. Have a great night, and I'll see you in class tomorrow.